Let me introduce our speaker today to you. He's Abe Chian. He was born in Taiwan, but he lived in Brazil for many years. He's a full professor at the National Institute for Space Research in Brazil, and also a professor at the University of Adelaide in Austria. He lives in Australia. So he got his degree in electrical engineering and space science at Cornell University, and then a PhD in applied mathematics and theoretical physics from the University of Cambridge, and also a PhD in economics from the University of Adelaide. His research interests focus on astrophysics and also plasma physics, and in particular turbulence in plasmas. He received a fellowship, a Guggenheim Fellowship, to spend some time at California Caltech, yes, and then he visited Meudon Observatory with a Marie Curie Fellowship, and in September he will spend 3 months in Nagoya University. So he's very active and collaborating with many different groups. And he takes pride in speaking, in being fluent in Portuñol, which is a merger between Spanish and Portuguese, because he has supervised many Portuguese and Spanish students. So today he's going to talk about nonlinear dynamics of space and astrophysical plasmas. So thank you very much for coming.
Okay, thank you. Do I need to?
It's okay. Thank you.
Okay. Thank you very much, Dr. Belo Rubio, for this invitation and opportunity to come to this prestigious Center of Excellence for Astrophysics. And I have a very productive interaction this week with Dr. Belo Rubio, and we hope soon you'll see our paper accepted. But today I will also mention some of the results. Okay, so I'm from Adelaide and IMPI, and today I will show you some of our results in observation, theory, as well as numerical simulations of nonlinear dynamics of space and astrophysical plasmas, and focus on turbulence and coherent structures and magnetic reconnections. So the outline of my talk, I will begin with give a brief background on magnetic reconnection and astrophysical turbulence, which is important perhaps for all of you and everything that's being done in this institute, because turbulence is a very important phenomena, even from the beginning of Big Bang until today, and evolution in all astrophysical systems. So I'm a basic physicist, so I try to develop, and my collaborators, we try to develop new techniques that can be useful for all of us. Yeah. And then I will start with an example of photosphere of the sun, and then I will move on to the expansion of the coherent structures. We call it magnetic flux rope, due to flare and coronal mass ejection, starting from lower corona all the way to near the Earth at 1 AU. And I will give using example of both space and ground observations to illustrate the entire process of how a star and the planet interact. We are very fortunate this year, 2019, because there are 3 important events that has occurred over the years. Yeah. First of all, the world is celebrating or commemorating 500 years since we the passing of the great painter and scientist. No, I think you all know about it. So 1519 is the year that Leonardo da Vinci passed away. But he left with us very important vision. Not only Mona Lisa, but turbulence. Through his drawing, which has reproduced in Physics Fluid 97, we can see from the left-hand side. So we can see it in this detailed drawing of observer of physical phenomena with Leonardo da Vinci, and he sees in detail how turbulence in the fluid, okay, behave through nonlinear interactions among coherent structures. Everything I'm going to say, he already saw it, yeah, and he see the presence of eddy or vortex motions, and not only that, he see the clockwise and anti-clockwise vortices interacting with each other. And so he sees that coherent structures is the base of the dynamics of turbulence. So it's order and chaos coexist in nature. And the second important event that happens this year is we are celebrating in a few months' time the first observation reported in monthly notice 160 years ago, 1859, of the first detection of flare in the universe. And this is done by Carrington, and he saw in a group of sunspots the sudden brightening of two patches. You can see two ribbons, two patches of intense bright and white lights. And this is one of the largest solar flare that has ever detected. And not only that, he also linked the solar flare occur on 1st of September to the big geomagnetic storms that was observed the next day in the magnetic fluctuations on the Earth. So that's the beginning of space age, of how sun and Earth interact and how star and planets are related to each other. And last month, I think we are all very excited, and some of the IAA scientists took important role in this first observation of black hole, direct observation, direct imaging. And Astrophysical Journal, as you know, in the April the 12th issue, have a detailed account of this observation. The next step of the team from the Event Horizon Telescope is to study variability, the dynamics of the plasma around the black hole. And I hope my video today, my presentation, will help the different groups in this institute to relate, now starting from the solar flare, and how this can help us to understand and predict what's going to happen and interpret the future observations of the EHT of the variability. And this can be related to black hole flares. Okay, so this is an APJ 2019 paper using Spitzer infrared, the lower time series, and also Chandra X-ray observation of the intermittent light curves of both the X-ray emission and also the infrared emission of the central black hole from Milky Way in the Sagittarius A region. So this, so you can see this is about this from 0 to 1200 minutes. Okay, so usually at least one flare from the black hole of the central region of the galaxy is detected. So it's a very common phenomenon. What is the origin of this flare? That is the key. Okay, and we can see that there's a correlation between the multi-wavelength observation of both X-ray and infrared. So there's 1 to 3, 4, you can see there's correlated observation of infrared flare, black hole flare, as well as the X-ray flares. What is the physical mechanism that produce the flare? So this is the topic of our talk. And I will see that actually the experts in this topic, they already use the information from solar physics as a base to interpret, to build model, to prepare for the EHT team to see, observe the variability of the black hole flares. And this is the model proposed by one of the experts in the field of black hole physics, Dr. Yuan, who did a PhD, I think, from Harvard. And so in Monthly Notice 2009, about 10 years ago, he proposed this model of black hole flare. So this is the black hole, and this is surrounded by an accretion disk and the corona. Okay? And because of the accretion disk and magnetorotational instability, coherent structures in the form of the magnetic flux ropes, surrounded by these loops, coronal loops, and you can see at the full point of the coronal loops, there's a two ribbon, very similar to what Carrington observed in the solar flare. Okay, and you can see there's an anti-parallel magnetic field, which is the preferential magnetic reconnection region. And it's the amplification of this region. You can see here, this is accretion disk, this is corona, and you can see that because of the emergence of the flux, magnetic flux, and injection of the both magnetic energy and magnetic helicity into the corona in this region of high concentration of magnetic energy and helicity, there's a reconnection that produces then the rise of magnetic flux rope. Okay, eventually this will lead to coronal mass ejection in the neighborhood of black hole. And because there's a current sheet, which is the region of reconnection that produces heating and acceleration of particle, then you have Brownstorm, and you have X-rays, and you have thermal Brownstorm, and you have infrared. And that's why we have, that's the interpretation today of a possible mechanism that can account for the origin of black hole flares. We did a numerical simulation of both accretion disk and solar dynamo. And in the long term, okay, we run the simulation. These are the 3D MHD simulation. The first one is a time series of the magnetic energy as a nonlinear evolution of magnetorotation instability. Okay, and we can see there's a similar to the intermittent light curve that we see in the black hole in the center of a galaxy. So there's a region of a high concentration of magnetic energy and the region of maximum, minimum, and which is not periodic because it's intermittent, it's chaotic, and it's nonlinear. And we use a synchronization characterized by Shannon entropy of the power spectrum and phase spectrum, to explain the origin of the on and off stage. So usually the intermittent light curves can be interpreted as intermittency. Intermittency means there's a region of peak of concentration of magnetic energy, kinetic energy, and the magnetic helicity, or in other words, reconnection. When there's a very strong localization of magnetic coherent structures, there's an interaction that produces transfer of energy, magnetic energy to kinetic energy, and that's why we have multi-wavelength observations. Okay. And the second example of time series is a numerical MHD simulation of a solar dynamo, which is a turbulence, And this is the magnetic energy. You can see similar to solar cycle. There's a region of intense emission related to a high level of magnetic energy, magnetic helicity, and this is the region of frequent occurrence of flare, and then this region of low-level magnetic energy activities. And again, we use Shannon entropy to quantify the origin of these coherent structures. Okay. Okay, now let's move to the second topic. And this week, I'm very happy and thankful to Dr. Bello Rubio for polishing our paper, which is under review in monthly notice. Yeah, and hopefully be published in a couple of weeks. Yeah. So we are now applying a new way to detect coherent structures. In order to understand turbulence that we are with now, it's very important to have a very precise techniques so that we can detect the coherent structures which give rise to turbulence, reconnections, and the emissions that we observe. Okay, so there's a review paper by Professor Haller in the Annual Review of Fluid Mechanics 2015, and which introduced this new techniques of Lagrangian coherent structures. And, we in 2011 we introduced this technique to astrophysics, and then the series of papers we have using observation and the simulation to step by step clarify how we can use these techniques for the astrophysical community. And I'm very honored that IAA, through Dr. Bello Rubio and Dr. Gosik, also Minlan Gosik, who was also a graduate of IAA. Now we are bringing the technique into a way that everybody hopefully can use to study the coherent structures in turbulence. So just without going into much detail in mathematics, basically we use a dynamical system as a background to detect coherent structures, and we apply the Lyapunov analysis to calculate finite time Lyapunov exponent, both forward in time and also backward in time, to detect the repelling, the green Lagrangian coherent structures, as well as the pink Lagrangian coherent structures, which are attracting. So this is just a diagram that illustrates dynamical flow of velocity field. You can see vortex flow here, and then this is the Lagrangian coherent structures, the repelling and attracting, and you can see there's also a third type of coherent structures which Leonardo da Vinci already told us. He called eddy, and we know today is vortex. Okay, the vortex flow is a elliptic Lagrangian coherent structures, and very important we detect vortex with precision. So there's a technique which Professor Haller and our group have been developing to detect vortex which is invariant for all observers. Through translation from rotation of frame, you will see the vortex, and that's very important. So you won't have a false detection, and so we call this objective vortices. And so this week we are finalizing the revision of a paper using data from Hinode mission. So its illustration, I have the velocity vortex in both Eulerian description as well as Lagrangian description. Eulerian description is what you are used to, the snapshot, the instantaneous image of the patterns. Okay, that's what we see in weather forecast. And let's see how good are this image that with the snapshot image that we see. So this is a MHD simulation of a dynamo, solar dynamo, for instance, and we have two different parameters regime of two vortex. They look similar. It's a snapshot. So eta is the magnetic diffusivity 0.01 is this is 0.05. Now we apply the Lagrangian coherent structures. Okay, first we detect the hyperbolic Lagrangian coherent structures, the repelling and attracting coherent structures. Yeah, so repelling is the green, attracting is red. So we can see basically we have a vortex here in the middle, which we don't see it, but we see it's surrounded by hyperbolic coherent structures. Yeah. But when we change parameters, magnetic diffusivity to 5, we can see the same vortex that we see is much more complex. These Lagrangian coherent structures are transport barriers. They are the preferential path of a particle divergent flow and convergent flow, as well as a trapped flow, that vortex. So we can see that Lagrangian coherent structure techniques provide us a much more precise skeleton of turbulence. It's not only the vortex detection, it gives us all the detailed dynamics and the structures that govern the divergent flow, convergent flow, as well as the elliptic flow. Okay? Let's see one example using Hinode data of an active region. This is one of the first flare observed by Hinode in 2006. And so this is a sunspot region, and we're going to focus on a region called Blach, where mainly we have a unipolar magnetic field of only about 12 megameters square. Okay, so we use the technique of local coherence tracking. I think you are correlation tracking. I think you're familiar LCT to obtain the image of the velocity flow. Okay, so we use velocity flow in order to compute the Lagrangian coherent structures. So this is the result of computation of that. This is only one example of that region where we have repelling coherent structures and attracting coherent structures. What is the Lagrangian coherent structures? They are the Sierra Nevada. They give us the reach of the dynamics. Okay, the valley, such as in the beautiful Costa del Sol, they are the valley regions of the dynamics of geophysics. Yeah. Whereas the coherent structures will bring us information of the divergent flow and convergent flow and give you precise quantitative measure of this rate of repulsion and attraction of the flow. And you can see, so this is the reef, which basically is the Massman-Lyapunov exponent. Okay, it's related to stability of the flow. Okay, so we can see this is the reach of the repelling Lagrangian coherent structures, which is related to QSL or quasi-separate layers, which are the preferential site of reconnection, magnetic reconnection, which is very important to study the active region. It's also called Q factor. So Q factor is related to repelling Lagrangian coherent structures and the magnetic reconnection, whereas the attracting Lagrangian coherent structures, we prove in the APJ letter, APJ 2014, that are related to, this is the line of sight magnetic field in this region. It's roughly, I think, about few thousand megameters, these structures. And we can see the reach of the magnetic field is correlated to the reach of the conversion flow. So this is divergent flow, this is conversion flow, and this is downflow region. So this is perhaps maybe one of the large granules, because this is less than 10 megameters, so this is not supergranule. Okay. However, now I'm going to show you one result of what we are going to publish, which is related to supergranule. So in 2017, my collaborator Eric Rempel and other collaborators, we introduced a new technique of detecting objective magnetic vortex. So there are coherent structures in terms of velocity flow. There's also very important class of coherent structures in terms of magnetic field. We can see from the model of the black hole flare is the formation of the magnetic coherent structures, magnetic fast ropes, and its interaction through magnetic reconnection that can produce heating, acceleration, and flares. Same as the solar flare as well. And so it's important that we develop also good tool to detect magnetic fast ropes, magnetic fast tubes, or filaments, or current sheets. Okay, so we introduced the theory and the method in 2017, and so far we are hoping very soon we find a way of apply to observation. We don't know how, but we'll find a way, maybe through numerical simulation first, before eventually the observationist people can provide us the way of applying it. So basically, in order to detect objective, now first, this is the velocity vortex, which was introduced by only a year before, 2016, by Professor Haller from Zurich. Yeah, so he introduced this very simple but very powerful way of detecting frame invariance velocity vortex by computing the Lagrangian average vorticity deviation. So basically, it integrates from initial time to time plus a finite time interval tau of this quantity of magnitude of the vorticity subtracted by the spatial average in the domain of the vorticity. Okay, and here again we are using the same previous solar dynamo turbulence. So this is the contour plot of this LAVD, and you can see there's a region of vortex, the black curve, which is amplified here. Okay, so here we are plotting three types of Lagrangian coherent structures. Now the repelling and attracting the hyperbolic, as well as closed elliptic vortex. In this case, it's velocity, and we use this initial this vortex. Yeah, if we use this vortex as initial condition, and then try to reproduce the trajectory, path line of the particles, we see that we have the vortex tube. Yeah, so this is it shows a very consistent and useful way of detecting objective velocity vortex. So these are two examples of vortex tubes. And in the same paper, then Rempo and Tao introduced the new techniques of detecting magnetic vortex, which is objective. And this is by computing the integrated average current deviation. Basically, so we take the magnetic field line, and then we try to follow the magnetic field path, okay, magnetic field line path, okay? And so we integrate from, for a given instant of time, you integrate from one initial space to the space plus a certain spatial interval, of the quantity which is a modulus of the current density subtracted by the average of the current density. And this subtraction is important to make sure we have an objective vortex. And this is the example. Again, this is the MT simulation of dynamo, and you can see there's a certain elliptic the curve here, and we use that initial condition to integrate the evolution, the dynamics of the magnetic field lines, and we see, in fact, we're able to detect magnetic vortex tubes. Okay. Now, coming to what we are discussing this week with here in Granada. So this is a product of IAA. I'm very thankful to Dr. Belo Rubio and his collaborators that produced this beautiful high-resolution data of solar photospheric turbulence in a quiet sun, in a center disk. Very carefully obtained data. And then now we are talking about a supergranulation region of 50 megameters. Yeah. So here we are showing the arrows are the horizontal velocity field. And you can see there's a big supergranule and several granules here. And in APJ 2018, Susana Silva et al. And our group, we applied the detection of a Lagrangian velocity vortex, and we were able to use a 15 minutes interval. We detect 7 vortices, and you can see these are the vortices. And the paper that we are going to publish in monthly notice is submitted, and we so far we received a very encouraging review. And so, well, maybe I haven't, since it's not published, but it's already available, our result in archive AstroPH. Okay, you can check, but we're going to revise in next few weeks and resubmit it very soon. So basically, what you are seeing of the previous slides, we now apply to the same region, and we are now revealing for the first time, we're seeing for the first time the skeleton of photospheric turbulence. Yeah, using hyperbolic, repelling, divergent flow, convergent flow, as well as vortex. And we see how the 3 coherent structures, Lagrangian coherent structures, relate to each other. Yeah, how transport barriers are created to trap the created valley of the flow that enable the formation of stable coherent structures, which is vortex. Yeah, so I think I'm very excited about this collaboration, and we hope this will help the community, not only solar physics, but in astrophysics, to understand turbulence. Okay, so now I would like to move on to the new stage. And I understand that the IAA is an active member of the Solar Orbiter mission. And the Solar Orbiter mission and other solar missions in the coming decades is going to bring us a new vision of solar wind, of solar physics. Yeah, of course, we know quite a lot, but not sufficient. I think lots of ideas will be changed. And this technique that I'm introducing can be very useful for both in situ data, which solar orbiter is going to collect as it see the approaching the sun, as well as the remote observations, such as the new European Solar Telescope that is being developed very soon through the active participation of IAA. Okay, so I think the timing is good, this collaboration, because hopefully we come back to the 500 years ago when we had the initial link between South America and Peninsula Iberica. This collaboration is important. We can produce very good result, and this is my hope. So basically now let's see how, now I won't talk about Lagrangian coherent structures, but I will see how we can detect turbulence locally. And we're going to see that the model that proposed for black hole flare is real, it works. And that's how we see turbulence in the solar wind, through reconnection between magnetic flux rope and its median. Yeah, so magnetic coherent structures, now, and its interaction now through magnetic reconnection really give rise to turbulence. Okay, so let's see now. So this is what's interesting is, only a few days before I prepared the seminar, I said, oh, it's how wonderful. The day after that, Dr. Rubio and his colleagues collect data of this quiet region. Now, he was very careful to make sure it's quiet. That's fine. But the sun wasn't quiet in other regions. Yeah, especially, there's a 2 sunspots we found out, and there's one of the sunspots happened to be just behind the limb. That's wonderful, because we see a very clear evolution of solar flare. And this is done through, when I was a Mahikui fellow, I just arrived in 2011, and we published in 2012, okay? And so we use a combination of a Nancy radio helograph, which produce radio image, okay, of the solar explosion, and also X-ray. Yeah, so RESI, it gives us X-ray information, as well as a SDO AIA instrument of the EUV. So now we can see, come back to intermittent light curve. So this dashed line is the onset of the flare at 12:14. So this is the 12:14. So the time series, this is a RESI. You can see the peak of the emission in soft and hard X-rays, okay? And this is the different wavelength radio imaging of the flare by the Nancy radiograph. And here we have the SDO EUV ultraviolet image of the erupting flare, the loops. So we have a different wavelengths of the EUV, so we can see, we have the 2 regions of the very hot plasma. So this is the million degree plasma heated by reconnection, current sheet that produce Bremsstraum, that produce non-thermal emissions, and that we detect here. And that we detect from the center galaxy. And soon we're going to detect from the M87. Okay, I hope maybe IAA will be the institute through collaboration with INPI and ADLE. Maybe we'll be the first one. Okay, and this is the very clear picture of what produced a flare. Okay, so you can see that there's erupting flare. This is a few seconds before that. You can see its expansion. And here this is the contour of the X-rays. So this is the X-ray. This is the flare region, the source of the flare. And this is there's a leading edge of the erupting magnetic flux rope. Okay, and upstream, just ahead, there's a sheath region. Okay, the shock is ahead of the sheath region. So the region between the shock and the leading edge of the magnetic flux rope, this is very important region. That's called sheath region, shock sheath region. And that's where the intense acceleration of particles, reconnection, and take place. And as a result, we have type 2 radio emission. Okay? And we show you now the details. So this is the model we published in 2012, ANA. So this there's a coherent magnetic flux rope, and this is the flare region, and this is the shock, and this is the region between the shock sheath, between the shock surface and the leading edge of the front boundary of the magnetic flux rope. So this region, we will see that this is the region of radio emission, and that's the Nancy radiograph. For the first time, we're able to image this. Okay, you can see. So this is you can see the dash curve is the leading edge, this one, and you can see the source of the radio emission, type 2 radio emission, exactly is right in this region, right in front of the rope, behind the shock. So this is the remote. But now we have solar orbiter. And the instrument from IAA is going to measure in situ. The same phenomena of coronal mass ejection, it will expand. It will reach the vicinity of Earth. It will intercept by solar orbiter. So we can test all these ideas in situ. Okay, so I will show you 2 examples. Okay, using the 1AU observation of several spacecraft Okay, same thing that we just described, remote observation, we see it is confirmed by the local observation. Okay, so this is a big flare that occurs in January 2005. This is one of the biggest ICME in history. There was the Carrington flare, and this is another big flare. Okay, so you can see the soil observation, the UV, you see the flare and the eruption. And so this eruption, now you can see that would reach the Earth. This is Earth. And so there's a lot of spacecraft upstream of the Earth ball shock. Basically, in the Lagrangian, at one point, there's an ACE spacecraft and there's a wind spacecraft. So we can monitor solar wind, the arrival of the ICME. The CME, when you go to the interplanetary region, it's called ICME, interplanetary coronal mass ejection. So lots of spacecraft were able to measure in this event, and the yellow region is the sheath region. So this is the shock surface. This is the leading edge of the magnetic fast rope. So this is the rope. Yeah. So I'm going to show you some results right near the leading edge. Okay, this we publish in, I show you first this one in APJ letter 2011 when I was visiting Caltech, and I go back now. Magnetic reconnection. I think this is something that you know, you work constantly to interpret how magnetic elements emerge, interact in photosphere, and how the inside supergranule and also in the boundary, the boundary of the supergranule, how the interaction of magnetic elements is important to understand the dynamics of photosphere. But reconnection, magnetic reconnection, is a very key and essential process to understand the astrophysics. So this is a picture from Nature 2006 by Fang from Berkeley and Professor Gosling from Colorado. They presented a very precise way of detecting magnetic reconnection in a solar wind. Okay? So basically, when you have an anti-parallel magnetic field, you produce a current sheet, the A1, A2. So this is called bifurcated current sheet due to reconnection. And you have also counter-streaming offing waves. That's very important because you have a spacecraft crosses the reconnection region. These are the signatures of magnetic reconnection. You see accelerated plasma, they call reconnection exhaust or jet. You see anti-parallel offing waves. You see also the bifurcated current sheet. So now there's a lot of evidence that this is the basic of solar wind turbulence. And we are quite confident this is what causes turbulence in different regions, including the active region, including the photosphere, both in the quiet sun and in active sun. So I'll show you briefly the two examples. Yeah. And I'm going to see how interplanetary turbulence is born. Because now we see right by the spacecraft, now reconnection really happening, and we see all these signatures as it happens. Okay? So we come back to the event of ICME of January 21, 22, 2005, the one I just introduced to you. So when there are three set of spacecraft confirm all these observations I'm going to show you. The ACE, the WIND, and also 4 identical spacecraft of the ESA, the cluster. So you have 6 spacecraft confirming, doing experiment of this process. That's very precise. So basically, I just summarize what we see. So here we have a shock arrival, and this is the leading edge of the magnetic fast rope, the magnetic cloud. Okay, and it happens that we see that this magnetic cloud actually consists of 2 magnetic fast ropes, because active region is very active. There are lots of coronal mass ejection is happening. And some are faster than the others. They can merge, they can interact, and one can even overtake the other one. But they merge and to form a big, strong ICME. And this is the case. Okay? So here we have a two magnetic fast rope, and we have a shock in front of the magnetic fast rope, and there's a sheath region behind the shock ahead of the magnetic fast rope. So we detected current sheets, and we see there are lots of magnetic, the pink region is the current sheet related to shear of the magnetic field. Okay, there's a precise technique to detect the current sheet. Current sheet is an evidence, a suggestion, there's a possibility of magnetic reconnection. And current sheet is a region not only of a connection, but particle acceleration, heating, and turbulence. Okay? And let's see whether this is true. So let's apply the state-of-art way of characterizing turbulence and coherent structures. Okay? So here we have power spectrum of, I'm going to just focusing only in 10 minutes data. 10 minutes near the front, we detect two current sheets. Okay, each one is only a few minutes duration because, okay, so the wing is a supersonic, very fast. Yeah. And we just use this, but cluster is very high resolution. Yeah, we got a million points, about million points for each data set to make sure the statistic is valid. So we use over million point data set to produce the power spectrum, and it's produced in the initial range exactly 1.7. That's the Kolmogorov's index. So the wing in the vicinity of the leading edge of erupting coronal rope, yeah, detected by several spacecraft and confirmed that it's a well-developed Kolmogorov turbulence. And there's a break here in power spectrum. Then this is the inertial range, and this is the dissipation range. Typical. Yeah, I think Leonardo da Vinci would be very happy that he saw it, but he didn't measure it. He's waiting for us to confirm. What is turbulence? Come back to Leonardo da Vinci. Come back to Lagrangian coherent structures. There's coherent structures, vortex. There's tubes. These are called coherent structures or intermittent structures because they are discontinuities. They are abrupt changes of physical parameters. And that's why they are called coherent, because they are distinguished, they are distinct, prominent structures compared to the background. Okay? And we can see this if you go to, you measure the 2-point difference, yeah, from the large scale, tau equals 200 seconds, 20 seconds, 2 seconds. You can see now there's a small fluctuation in large scale. As you go to smaller scale, you can see large fluctuations. And this is the intermittent structures. If we build a histogram, the PDF of the magnetic field fluctuations, large scale, you can see the yellow line is Gaussian. As you go to smaller scale, you can see the deviation for Gaussian becomes stronger, and this is called leptocratic, non-Gaussian PDF. Okay? And if you now use the state-of-art way of characterizing turbulence using higher order structural functions, yeah, the third order is skewness, fourth order is kurtosis. Now, so these are much more precise way of make sure that we have turbulence. So this is a scaling function, and you can see this is a monofractal curve, and this is multifractal curve. For each moment of the structural function, there's a different index. And that's why we don't live in a monofractal world. We don't live in a Gaussian world. We don't live in a noisy world only. There's a coherent process. There's a nonlinear deterministic process in addition to random process. So coexistence of stochastic and deterministic physical process together produce the universe that we live in. And why? Because there's coherent structures. There's magnetic flux ropes. There's vortex tubes. And they interact to produce turbulence, that produce X-rays, to produce radio emissions. Okay? And this departure is a very state-of-the-art way of showing, okay, solar wind near the leading edge of the magnetic flux rope. No, starting from the sun when it comes here, and it can reach up to the edge of solar system, as verified by Voyager mission, because they are stable. These are coherent structures. They don't live just a few days. Sunspot is very stable. It can live for several days, even several weeks, because they are stable. Cyclones, they are very stable structures. Order and chaos together, build the world that we live in. Yeah. Okay, so let's see now second, this is the same event now. We can see that there's magnetic holes related to the reconnection. These are the signatures that you can use to analyze your data. What are the signatures of magnetic connection? You can see depletion of the amplitude of magnetic field. You can see jet, magnitude velocity. You can see jet. Okay. You can see also bifurcated current sheet. So this is the bifurcated current sheet. The picture that Nature 2006 by Fang and Gosling is seen in real data. And this will be seen for sure by solar orbiter. Okay? And in addition, it also detects to the magnetic velocity and magnetic field in 3 component and velocity component in the LMN coordinate. That's much more precise to see reconnection. We can see counter-streaming of in waves. All the signature require to prove is magnetic connection. We see it in situ. Okay, right at the edge, near the boundary. Okay. So the final example I'm going to give is we live in a world where coherent structures interact with each other. I keep repeating, but that's what we see. Yeah. So these are all the first time that we see this with such a clarity, and we see turbulence related to reconnection. So these are intertwined. This is the base of nonlinear dynamics of plasmas, not only in space, in solar system, but also in astrophysics. We can now, with this observation, and let's see, what about when you have a 2 magnetic flux rope in solar wind, and we can detect them, and let's focus on the interface region, interaction region between 2 magnetic flux ropes. And that's what Leonardo da Vinci saw. 500 years ago or before he passed away, he see and he write, okay, it's interaction of the eddies that produce turbulence patterns in the fluid. And that's why we see this is 2016. Okay, 2016 APJ. We now we took the same event analyzed in Nature 2006 by Fang and Gosling, and now we understand what is the origin of the reconnection they studied. So we used very careful techniques. Yeah, through international team of experts, we are able to detect in that event there are 3 magnetic flux ropes or ICMEs. There are 3 ICMEs. Sorry. Okay, let's come back. Okay, so this is the first rope, second rope, and third rope. So this is about it's a Julian day 32, 33. Yeah, so this is about just over 1 day data, similar to your data of the quiet region. So we were able to detect 3, 1 intermediate scale ICME, 2 small scale ICME. Especially, we were able to see this small region where the 2 magnetic flux ropes interact. Okay. Now let's see what they do when they interact. So what we do, we divide this time series into 5 5 regions, indicated by 5 different colors, with the same statistics of 30-minute interval. Yeah. And again, I think we use a cluster with a very high data to validate the statistics. And we were able to confirm the paper I showed you in the beginning. The origin of coherent structures is due to amplitude and phase synchronization in the nonlinear multiscale interactions. We call it wave-wave interactions. We have fluctuations, but they can synchronize in amplitude, in phase, and when they synchronize, they produce coherent structures. Okay? And coherent structures, we already seen its origin. And so this is the techniques for the kurtosis, and this is called phase coherence index. You can go to the detail of our paper. And lots of people now applying this phase coherence index. It's a surrogate data method to prove to measure the degree of coherence, and people are using in interstellar turbulence as well. So of the 5 regions, we see this stand out, and this the curve refer to this region, refer to exactly this region where is the interface at the rear boundary of the second rope when it's interact with the leading boundary of the third rope. So this purple region is this purple. You can see there's high degree, this is Gaussian, okay, and this is so this is the kurtosis, the 4th order structure function, and this is the quantification of degree of phase coherence among multiscale interactions. We can see that this region produces the strongest origin of solar wind turbulence. So this is where, and you can see now again we use a scaling exponent in terms of structure function to show that exactly this curve refers to this region. So my last slides is showing you now the evidence the same way we did with the one example of the ICME of January 2005. The leading edge of the magnetic cloud produced signatures of reconnection and cosmograph turbulence. The same technique we apply to this interaction region between 2 magnetic flux ropes. And we see exactly similar behavior. Okay? So this is the summary. You can see the modular magnetic field. You can see depletion, magnetic holes, okay? Because you have an antipolar magnetic field. So modulus have to go through the minimum, okay? And you have jet magnetic velocity due to reconnection, the transformation from magnetic energy to kinetic energy. And this is particle acceleration that produce electrons that can produce Brownstorm, X-rays. It can produce thermal Brownstorm, which also can explain the infrared of the flare in the back from the center of our Milky Way. Okay? And we see also from the magnetic field component and the velocity component, the signature of counter-streaming Alpha waves. We see the signature of bifurcated current sheets. Spacecraft measure 2 magnetic sheets the way it should be. And we use 2 different techniques, and we use, because we have 4 spacecraft, so we can use coulometer. We can compute current using 4 spacecraft. And so we use 1 spacecraft and 4 spacecraft techniques to confirm that there are 2 current sheets. And this is this region is a region of reconnection. And we can see there's enhancement of density, and there's an enhancement of plasma heating. And this is the way we're going to use as a base to understand the origin of nonlinear process that occurs in different regions of the sun, different timing of the sun. And solar dynamo is turbulence in all solar cycle, because solar cycle is chaotic, is turbulent, is intermittent. Same as the light curve of the emissions from lots of astrophysical objects. So I summarize now my talk. The 3 points that I'm making, and this is a result of 2 solar cycles of very enjoyable but hard studies. And the main collaborators of mine are Enrico Rempo and Rodrigo Miranda and Susana Silva from ITA, INPE, and Universidad Brasilia. And also Felix Bolotto from Universidad Concepción and Pablo Muñoz from Universidad de La Serena, both Chile. Okay, so they are all my students, but now they are my boss. Okay, but we have a very productive interaction. Although I'm in Australia, we produce. We just published a paper I've shown, but I didn't go into detail last week, of a 15-page detailed theory of objective magnetic vortex in Physics Review E. Okay. Today, Susana Silva, who is the first author of the APJ letter, the first detection in using your data. Okay, last year. Now today she is arriving in Sheffield. The working group of the Swedish Solar Telescope 2. One is headed by Dr. Velo Rubio. So they are interested to use our techniques, and that'll be very useful if we can, different working groups through international collaborations, we can speed up the application of the state-of-art theory, simulation, and nonlinear techniques to advance our understanding of the turbulence. So in summary, now space astrophysical plasmas are governed by nonlinear dynamical process of magnetic reconnection and intermittent turbulence. I hope you're convinced. I wasn't convinced until we wrote these papers. In addition, now with the new techniques of Lagrangian coherent structures, we have a new way of helping Leonardo da Vinci to clarify what is the drawing that he was making. We can use the Lagrangian and the Poincaré help, try to bring out really the detailed nonlinear dynamics of the coherent structures and turbulence. And this will provide us a much more precise way to detect transport barriers, to understand how the plasma behave, and to detect objective velocity and magnetic vortices. That's why this week we are trying to see, but at the moment, magnetic vortex seems not easy, but we never give up. I told Dr. Velo Rubio, I am Espanol, yeah, because yo hablo portuñol. And I like mente la mancha. We have to fight against wind, against the impossible. We must dream, transform dream into reality. And I think this is shared by all of you because you're all Espanol. Yeah. And most important, sun and heliosphere. Now, provide a unique laboratory to study flares, coronal mass ejections. Now, with high precision, new telescope, available telescopes, as well as past ongoing missions and future missions. And this information is give us a confidence how to interpret similar process of astrophysical plasmas that occur in AGN blazars, galaxy center, okay, binary black holes, neutron stars, and this is a detection of gravitational waves, microquasars, gamma ray burst, and the star formation, and proton planets. And probably through this way of international collaboration and multidisciplinary approach, we can find a home now for in some exoplanet that we can confidently arrive one day, now without getting burned. Okay, I thank you for your attention.
Thank you very much for your talk. It was very interesting, and you covered a lot of different fields, which I think it was very good. So is there any question or comment you want to make?
This opportunity, I came from far away Australia. So the kangaroo had to jump thousands of miles. So.
Francisco?
The applications of these today are all about plasma dynamics, but in principle I think this technique can also be applied to fluid dynamics in general. So my question is, are you aware of any application of this technique to the study of the dynamics of planetary atmospheres? And if so, how does it improve over the use of more classical techniques?
So in this review of Lagrangian coherent structures, Professor Haller has already answered your question with examples of the giant spot. Yeah, so it works very well. And so I'm looking for partners who are interested to apply to Cassini and the data of Saturn also. We don't know how to predict cyclones. Because of climate change, I think the weather forecast is getting lost because they are in the nonlinear dynamic is coming into a regime that they don't know how to forecast with precision. Now the flood level, the rain levels, the vorticity, the things, and LCS is the state-of-art technique that can help us to detect the atmospheric dynamics. And so in this paper, Annual Review Fluid Mechanics, yeah, you can see example, and they publish very detailed papers, or details how they apply the technique to detect the vortex, the red spot in Jupiter, and their work also in Spain. I told below. I am a stranger to LCS because Spain is a mecca, is the capital of LCS research for ocean. So there's a strong group in Spain, in Madrid, in Barcelona, especially in Mallorca. Yeah, so you have so you can easily interact with them. But I'm happy. I am a mathematician. So I'm interested in good application with that we can produce good impact. Yeah. So this is a very huge and fast-growing field. Astrophysics, we are way behind. Whereas in atmosphere, especially in ocean, you have hundreds of people now working in this. They are already integrating into weather prediction. Now, for planetary science, there's only this work by Haller and his collaborators, and they publish one or two or three, but they are not planetary scientists. They are statistical physics and mathematicians. So I think that's why I'm convinced through my experience this week, we must get out of our valley. You have to go over the transport barrier. Yeah, you have to, and that's the question, that one of the questions you mark. Can the magnetic elements cross? Yes, they can. Because this is only the simple picture of transport barriers. There's details of mixing, chaotic mixing. That's why boundary is very complicated, because boundary is not a boundary. It's a dynamical process. Now it evolves. And vortex, again, it's evolving constantly, especially in the eyeball region. No, because that's where the big rainfall comes in. And it's the most stable region is the most impact. Like tsunami, it's a solitone. It's a stable, but when the nonlinear coherent structures impact the background, it produces very strong perturbation. Yeah. So you can write to me also. I have a full collection of literature, and I think if we can apply to exoplanets, and everything I discussed today actually is very important for exoplanets. Yeah. So I didn't come into details, but the magnetic reconnection between two magnetic flux ropes in the stellar wind produce exactly the dynamic pressure pulse. And this can get rid of the atmosphere. And lots of exoplanets are naked and no atmosphere. And maybe because of during the protostellar evolution, there are lots of CMEs. And because of the reconnection produced dynamic pressure pulse, and they just sweep out the atmosphere. And maybe that's why Mars and Venus is without atmosphere. Yeah. So I think, yes, it's very important and it's ready. It's not difficult. And I think there's no work apart from Harler's group, and they are not in the field. They just want to use as example, and it's included in the review.
Any more questions, quick questions? If not...
Can I ask in Spanish? Or any Brazilian here? You said there's some Brazilian? No Brazilian?
Yeah, no.
Not in torcida. I thought I was hoping some veggie amarelo torcida will appear, but they are writing papers, which is good.
Okay, if not, I think we should stop here. Professor Chian will leave today, but if you want to contact him, please come and see me, and I will provide you with the contact details.
And I'd like to give you one present. No, I already left the present, very good present with Dr. Belo Rubio. I edited a very good handbook through Springer. Written by 20 group of the founders of space physics. Okay, Eugene Parker, Lanzarote, Eric Priest, Nishita. They write their lifetime knowledge of their field, and this is a very expensive book. But please don't tell Springer. Okay, I can give you free, but please use it because this is their life history, their view is published 2007. Of course, you have to update it with it, but I'll be very happy if you knock the door or you send an email to either me or Dr. Rubio, and you can, among your friends, don't spread out too much, but those people you think can be useful. It covers Kiefelson, the PI of the Galileo mission, wrote the chapter. Yeah, so there's a neutral atmosphere. There's even comet interaction. A student of our famous professor wrote the comet. Yeah, and so I think this handbook it should be useful for you. So I like to give you in Portuguese it's called presente or regalo. No, but I hope you use it, and that I'll be very happy. Okay.
I have that handbook. So